Hello, everyone. Welcome and thank you for joining our webinar today. My name is Scott Siphon with Moxa, and I'll be your moderator. As you know, we'll be discussing the topic of deploying Azure Machine Learning and Moxa IoT Edge Gateways. I do have just a quick couple housekeeping items to mention. First off, if you have any questions during the webinar, please feel free to submit them through the questions pane. Depending on the question, we'll either address it directly through the chat window or during the Q&A session at the very end. The other question that we get is, can we get a copy of the recording? The answer is yes. Anyone that registered will receive an email tomorrow from Moxa with a link to the webinar recording. So please be on the lookout for that. Okay, now let me introduce our presenters for today. First off, we have Robert Jackson, who is Moxa's Global IIoT Partner Manager. Robert has over 15 years of experience in the industrial industry and is currently responsible for the development of our IoT partner ecosystem. Alongside Robert, we're joined by Ted Wei, who is Senior Program Manager of the AI and Advanced Architecture team at Microsoft. In Ted's current role, he focuses his efforts on the hardware acceleration of AI algorithms, both in the cloud and at the edge. Thank you to both of them for being here today. With that said, I think we're ready to go. Let me hand things over to Robert to get us started.
Thank you, Scott, and welcome to the webinar, everyone. We're really excited to have you, and we're excited to share today some new developments that include deploying machine learning, also how to enable device lifecycle management for your Industrial IoT Edge Gateways. And then finally, we will conclude the webinar with some recent case studies to hopefully inspire you to move from a proof of concept to a real Industrial IoT deployment. As we meet with key customers and collaborate with them on their industrial IoT applications, one clear need has emerged. Customers across oil and gas, energy, industrial automation, and the transportation industries need to enable device lifecycle management in order to realize the full scalability and potential of their industrial IoT applications. Based on these customers' feedback, Moxa has developed the 7 principles of device lifecycle management. First, to help scope the challenge, many customers speak about device management. However, if you really evaluate the complete application, you first need to take a step back and consider the entire device lifecycle. First, you need to plan how your organization will group, secure, and enable access to large numbers of IoT devices. Then you need tools to securely authenticate and provision network devices. As a next step, you need to provide device updates, configurations, and application specifics to the purpose of each device. These first 3 steps can get you started, yet for most of a device lifecycle, you need tools to enable remote device management. You also need to ensure you're monitoring for security and deploying security updates and application updates. Finally, at some point, you'll need to make changes, and this might be due to changes in the application requirements or simply because you want to replace existing hardware that has reached the end of its life with a form, fit, and function equivalent. When we talk about device lifecycle management, we're looking at this broad, holistic picture. We've also identified 7 principles, and these principles are essentially the technology building blocks which are required. This device lifecycle process is something Moxa is working closely with Microsoft and other major cloud vendors to make sure we're directly integrating with key cloud technologies. The first one is a capability to enable provisioning, and specific tools like Device Provisioning Service from Microsoft are critical for us to integrate with. I'll go deeper into this in the next couple slides, so let me go ahead and cover some of the other core principles. Another key area, of course, is still commissioning, and this commissioning allows you to enable specific hardware profiles based on the device name or geographic location. The third area is the ability to remotely update software based on Linux Docker containers. The fourth area is to be able to enable hardware-focused device management for networking, cellular, and industrial protocols. Then another key principle, and often one of the most important, is the ability to deploy remote security patches. When we think about the long-term availability of a device, we care quite a bit about ensuring our customers have access to and can deploy these security patches over time. Then, of course, we have to look into the need for major software upgrades. And here we're working to enable over-the-air updates of lower-level edge software components, often referred to as daemons. And then finally, a critical step is to ensure we can recover damaged systems or address more systematic security breaches by able to make a complete update to the Linux operating system kernel. I'm excited to share Moxa and Microsoft are working to ensure all of this can be supported on an over-the-air cellular network. I also think you'll see that we've really scoped this to be the broadest application and applicability of the needs we're seeing from key accounts and key customers. To go further into the details, the provisioning step is key to ensure security and the appropriate application-specific logic is deployed. One of the key technologies we're working closely with is the Azure IoT Hub Device Provisioning Service, often just called DPS. DPS is a service that enables end customers to create logic for how their applications will be deployed. The DPS service specifically detects when new hardware is connected to the network. It helps establish the initial security credentials, whether this is an X509 certificate or a SAS TPM token. Then based on logic defined by the customer, it determines based on either perhaps the device location or preset rules if it should connect to the closest Azure IoT Hub or to a specific hub for security or deployment reasons. Then finally, it defines the initial hardware profiles that should be deployed. Perhaps it's a heat exchanger, and so the hardware needs to have that application-specific knowledge deployed on original provisioning and commissioning. We're seeing many customers who want to have more control of their networks, and the provisioning process is included in this control aspect. Here, we're working to fully integrate into the rapidly expanding capabilities of these cloud architectures, and also working with Microsoft deep into their roadmap for how device provisioning service can work for us. After provisioning and physically commissioning the hardware, the next step is to remotely install software containers. To start with a single deployment, Azure IoT Hub has a profile for a device with a software, for example, let's say Modbus communication, has another container with Azure Stream Analytics capabilities, and then of course, custom code that the customer has developed and defined can also be created in containers. In order to deploy this code, a deployment manifest is created. The Azure Container Registry deploys this manifest and also the code contained in each container. This can happen with one device, as I've kind of highlighted here, but most importantly, this can happen with thousands of devices at scale through scripting. One key prerequisite of this, however, is you need to ensure Azure IoT Edge boot software is already installed on the hardware. This boot software is often referred to as the daemon. Here, Moxa was one of the first partners to join the Azure IoT Edge Partner Program, and we can ship hardware with this boot software already pre-installed on it. In addition to supporting customers who are asking for device lifecycle management, we are also working side by side with Microsoft to fully integrate with Azure IoT Edge to enable the edge analytics, security, and data analysis you require closer to the edge. We'll also shortly hear from Ted Way on how we can even add machine learning and look forward into solving more advanced applications with this integrated architecture. After provisioning, commissioning, and remote software updates, many customers are focused on how to remotely manage devices in the field at scale. A key technology to enable this device management are module twins. A module twin is a software representation of the hardware state that is located in both the cloud and also at the edge. So again, let me start with a simple application of just one device. Here, the desired property located in the IoT Hub is communicated to the module twin located on the Azure IoT Edge device. This desired property change request from the hub represents an action for each individual hardware device. If the hardware device implements this change correctly, it can communicate back to the IoT Hub through a reported property, and this reported property synchronizes both the hub and the edge. This is a really important technical aspect. In order to do this type of mass device management at scale, you need this type of handshaking architecture where you can set the desired properties of thousands of devices, allow them to operate asynchronously and update at the rate that's appropriate for them, For example, they might not want to update the Ethernet port if they're actually using that to communicate. Or they might not want to reboot the device if they're in the middle of an actual operation or a task. So here it gives an architecture where the hub can generate centralized commands to make changes at scale, but each edge device can decide when and how to effectively operate and make that change. And then once successful, communicate that back to the IoT hub. So at scale, this really does enable you to change groups of devices to efficiently share and then update those results back to IoT Hub. Another capability is you can also invoke direct methods. And these are calls that can request a direct change to the device itself. A good example of this use case is you could use a direct method to ask a device to directly reboot itself. So pulling all of these capabilities together, this block diagram shows the technical architecture of how all of this software ends up installed on hardware. At the bottom, we have the Moxa Industrial IoT Edge Gateway with ARM or x86. And then we also have Moxa Industrial Linux that can offer you up to 10 years of support, as well as Debian operating system as the base. Azure IoT Edge is then installed, and you can also add services like Azure Stream Analytics, industrial protocols, and Moxa's device management. In addition, of course, we can support customer-defined applications, and all of this is installed into a Linux container on the IoT Edge Gateway. In the Azure IoT Hub, you have the device and workload management capabilities, and also integration through module twins for Moxa hardware management tools. On top of this, you can layer on storage, analytics, and dashboard capabilities of Azure. So to talk a little bit more about our software, we offer ThingsPro, and essentially ThingsPro consists of two key parts, a local user interface and a RESTful API. The local user interface, or UI, is essentially a web browser that's available from the local hardware. It provides an easy-to-use option to see device information, and then you can also set up the device configuration, including networking and cellular options. You can also configure southbound protocols like Modbus, and then easily configure connectivity to the Azure IoT Hub. However, for many more advanced applications, customers need a way to programmatically access their hardware, and we have the capability through our RESTful API to enable this. This RESTful API is really intended for cloud integration, and with the combination of module twin supports, which I just spoke about, you can easily configure and manage hardware at scale through the cloud. Moxa is working closely with Microsoft to enable direct integration of this device management and module twin capabilities. Also to deliver remote over-the-air updates, which again can be triggered by module twins, and also ensure lower-level Linux software packages can be managed through module twins and the Microsoft JSON file structure and format. If you'd like to learn more about this advanced integration and capability, please feel free to reach out to us. It's quite an exciting area of development. So with that, we'd like to also get some input from our audience, and we've got our first poll question. So what we'd like to know is which of the following technologies have you used or evaluated? You can select multiple, but we'd like to know if you're using Azure IoT Hub, if you've considered or are using Azure IoT Edge, if you've looked at Azure Machine Learning for doing models in the cloud, or if you've evaluated actually deploying Azure Machine Learning to the edge. And again, you can select multiple responses, and we really appreciate everyone's feedback here. It gives us a good sense of how to focus to address your market needs. We'll give everyone just a few more minutes. Please go ahead and on your screen select one of these options. We'll then get to see the results of the entire audience. Okay, it looks like we're closing the poll, and this is great to see. This is what we'd expect, although I'm excited to see the number of you also looking at Azure IoT Edge. So we're really excited to work with those customers who are leading the technology change here. Exciting to see too, the Azure Machine Learning in the cloud, and then We understand deploying machine learning is still a really advanced topic, so we understand that response and that makes sense. We're here to share a little bit more today, but also it will take a lot more collaboration with key accounts out there to help determine the right approach and applications. So with that, thank you for your feedback. It is now my pleasure to introduce Ted Way, Senior Program Manager at Microsoft, and he's going to share some of the latest developments with Azure Machine Learning.
All right. Thank you very much, Robert, for that comprehensive overview of IoT and just for the great partnership that we have with Moxa. And as Robert mentioned, I'm Ted, and I work on the AI and Advanced Architectures team here at Microsoft. And I really thank you for the opportunity to be able to share with you today. Robert talked about IoT and edge devices, and I'll focus on how to add intelligent capabilities to those devices. And this starts with a data scientist building a machine learning or AI model. And to do that, these are the building blocks for that process. The first step is to build and train your machine learning or AI models. And you may be training a classical machine learning model. For example, maybe the data from your sensors is being collected and you want to do something like energy forecasting. How much energy will I need? Or maybe you might be doing predictive maintenance, taking in all that data from a machine and trying to predict how much longer that machine will require before it needs maintenance. If you're doing some things around deep learning, building these AI algorithms, maybe you're taking pictures of products as they come down the assembly line and using an AI model to evaluate that picture and determine whether there's a manufacturing defect in that product based on visual inspection. Or it could be even taking in images from cameras that you might have in your site or in your factory, and then being able to evaluate, are people wearing the right safety equipment, or are there objects in places where they should not be? Those are some of the things that you could do with these machine learning or deep neural network AI models. With all of these algorithms, they all require some form of hyperparameter tuning. So our AI platform also gives you that capability. So just like you might need to calibrate machines for the optimal way of using them, AI algorithms are the same way. You would also need to be able to process and calibrate and tune the parameters for these models so that you get the best accuracy and the best predictive power. A lot of what data scientists do are essentially running experiments. They take the data that you have and they want to try to find the best algorithm, the best set of parameters, and then be able to see which set would give you the best result that you're looking for. And so keeping track of all of these experiments and pipelines is also super critical. After you've trained a model and after you have a model that has pretty good results, then you would need to deploy that. And the way we deploy it on the AI platform is to package everything into a Docker container. Docker is an open source format, and the model is fronted by a RESTful API. So now you can send data to this API, whether you deploy this model to the cloud or to the edge, and then you can take that model to anywhere that could run Docker. The benefit of this is that all of the dependencies are in that Docker container. In the open source world today, there are a bunch of different libraries and they all have dependencies on each other. So you may end up creating a machine learning model that uses version 1.2 of this library. I may be using a model that uses version 1.1. And if we were both to deploy our model onto a machine, we would be in conflict because we don't know what version that machine should have. Is it 1.1 or 1.2? So what we do is we just put everything in that Docker container so that in my container, I have version 1.1. In your container, you have version 1.2, and the containers can both live on the IoT Edge device and be able to run the model that they need to do. Finally, we're seeing a really, really big push to incorporate the DevOps work, the DevOps cycle and process into the machine learning flow. software development has come a long way. It's very, very mature, and people have been doing software development for decades. And there's been a rigorous process to be able to keep track of source code, to version it, to have a continuous integration, continuous deployment pipeline. All of these things are very well known in the software development world. In the machine learning world, though, it's still kind of ad hoc, still kind of wild west, where people, data scientists might be training a model, they might deploy it in production, and then might have no idea of who created that model. So what we enable you to do on the AI platform is to keep track of your model so that when the model's deployed to the cloud or the edge and you're seeing the results from that model, you have model lineage. You can trace that model back to the Docker image. You can trace it back to the model source code. You can trace it to the data scientist who created that model. You can trace it to the training data that was used to train that model. So all of this is integrated in DevOps. And all of this is available as a set of cloud services on Azure. And the set of cloud services is accessible via a Python SDK. And with this set of services, we enable you to prepare data. We have a data preparation SDK so that you could get data into the right shape and the right form to be able to feed into your model. You can build the models and train them, as we talked about in the previous slide. You can manage the models. So in the data science DevOps flow, models are the unit of just like source code might be the things that you track in DevOps. Also keep enabling you to track the experiments and to deploy the models. So this set of services is available on the Azure platform for you to be able to do all of these things. So the Azure Machine Learning service is really just to help you boost your data science productivity, because you don't want to worry about all of the underlying tooling and the infrastructure. We want to enable you to just focus on the things that matter most to you, which is essentially taking your data and getting the value out of that data. We want to help you increase your rate of experimentation with the compute that we have in Azure. So you only pay for the compute that you're running. Your data scientists might be spinning up clusters of machine and trying out lots of different models. And then when you're done, you can just spin them down and not have to pay for it anymore. But that gives you the capability of running a lot of different experiments to try to find the best model. And again, being able to deploy and manage your models everywhere in the Azure ecosystem. Theoretically, you could take the Docker container, you could run it on Google Cloud, you could run it on AWS. Nothing's preventing you from doing it. Of course, we hope you don't, but you can. But you do lose that model lineage if it leaves the Azure ecosystem. So once you deploy your model in Azure or on an IoT Edge device, we can still keep track of it and trace it back. But once it leaves the ecosystem, we won't be able to track it anymore. Some of the other things that are part of the platform is something that's called automated machine learning. And automated machine learning came out of a need in which we were looking at how do we apply AI on AI. And what this means is that if you have some data, what a typical data scientist would be doing is trying to understand the data, trying to do a lot of experiments to try to run on that data to see what type of algorithm would be best applied to this data. What kind of parameters can be used with this data? And that's a very time-consuming process. So with automated machine learning, what you can do now is take the data, apply your constraints, define your goals, and then we run a process that searches through a set of algorithms and tries a set of parameters to try to give you the optimal algorithm. And this would be useful in which you might have a lot of models that you need to retrain constantly, and you just want to get some good result with that model. But it really is to help the data scientist boost his or her productivity. And it actually performs pretty well. Many of you may be familiar with Kaggle. Kaggle is a website, is a competition, and basically they have different competitions where they have data sets, and then data scientists would be trying to train models that would have the best accuracy. And these are just data science competitions. So what we do is that with automated machine learning, what we did was we participated in one of the competitions, we downloaded the data, we applied automated machine learning on it, and then submitted the results. No human intervention at all. And we got in the top 5% of everybody who submitted a model for that competition. And this just gives you an idea of the power of automated machine learning. It's not going to give you as good of a result as something that a human had fine-tuned and optimized, but at least it'll give you a general direction of where to optimize. So that's automated machine learning. And as I mentioned, the managed compute, simple deployment, DevOps, and then I'll talk next about the open source frameworks and our Python SDK. In terms of popular frameworks on the Azure AI platform, we support all open source frameworks, and that enables you to use the favorite framework that you like. Most data scientists today, if they were doing deep learning or an AI application, would like to use TensorFlow that came out of Google, which is now open source. A lot of other data scientists, more and more, are using PyTorch, which is also open source and came out of Facebook. But everybody has a framework that they may be more partial to, that they may be more used to. And we support them all. Now, one of the downsides of so many frameworks is that each one of their frameworks also has a specific runtime. So maybe you hire 2 people out of school. One of them really likes to use TensorFlow. Another one really likes to use PyTorch. And now they're generating and creating their AI models using these frameworks. And now on your edge device, you have to support running both frameworks. And that just becomes a big problem as more and more frameworks are crowding the field. What we've done with Facebook is come up with the ONNX format. ONNX is the Open Neural Network Exchange format. And I like to think of it as the PDF of AI frameworks. So just like if you were in an office, maybe you use Microsoft Office, maybe your coworker likes OpenOffice, another coworker uses LibreOffice. How do you interchange documents? Because all of these tools may be generating things in different formats. And so we can all align on something like PDF. And if we agree and we say, okay, we're just going to convert whatever we do into PDF, and now we're able to interchange our documents because we all agree on PDF. And that's essentially what ONNX is. ONNX is this format. It's being adopted by more and more companies so that whatever framework you use, you would be able to convert that model into this ONNX format, and then it would be converted back into other frameworks. So that's the first part of ONNX, this PDF, or the representation of the machine learning model, the AI model. The second part of ONNX is the ONNX runtime. So now on your edge device, you could run the ONNX runtime, and that can run any ONNX model. And the benefit of this is you can decouple the deep learning framework from the runtime. So again, if a data scientist creates a model using PyTorch or somebody else uses MXNet, which came out of Amazon, that can be converted into the ONNX format, and then you just have to worry about running ONNX on your machine, and you don't have to worry about the framework du jour. So we have support for any of these open source frameworks, and we also have support for ONNX and the ONNX runtime so that we're able to run any type of model on the edge device. All the services are accessible via a Python SDK. Python is the language of choice now from students coming out of school and from data science practitioners. Python is a very, very versatile language, and a lot of the open source libraries are pretty much Python first. R is still very popular. The R language is popular among statisticians and mathematicians who do some very, very deep analysis on them. But Python is what we're seeing becoming very, very popular. So we enable you to use a Python SDK in your favorite IDE. I know Microsoft always had a bad habit of creating solutions and forcing you to use them. We've heard your feedback, and so basically what this means is if you or your data scientists like to use PyCharm, if you like to use Jupyter Notebooks, Visual Studio Code, or some people even the command line, you can access these services through the SDK instead of any other fixed IDE. Because it's an SDK, we can also integrate with other services like Azure Databricks. For those who like to use Spark and Databricks, we have integration with that. And we have the flexibility because that same Docker container can be deployed to the cloud and scaled out using something like Azure Kubernetes Service, or it can be deployed to that edge device, as Robert had mentioned. And again, as a productivity company, we really want to help you accelerate your machine learning and AI journey so that you don't have to worry about the underlying infrastructure, but really just focusing on the high value work. And so just taking this back to the architecture that Robert mentioned, in Azure, using the AI platform with Azure Machine Learning, you're able to create these machine learning models packaged up in Docker containers. And so you can deploy them to the cloud and run them in the cloud, or deploy that same container to the Azure IoT Edge device. So using a device such as a Moxa x86 Linux device, this device can be, this Docker container can be deployed to that device, and it could be integrated in a pipeline. So you're ingesting data from a sensor. That data may be going through a stream analytics workflow. It may then be going through a machine learning predictive model, and then the result can be used to, say, control the machine, or it could be sent back to the cloud to take further action or to be shown on a dashboard, for example. So that's how everything integrates in the cloud and on the edge. In terms of support, from the Azure Machine Learning perspective, we enable you to create these Docker containers and deploy them onto Linux devices running x86, x64 CPUs. Azure IoT Edge also supports Windows, so you could create your own specific models to deploy them onto Windows devices. What we've also seen is that customers may have a Windows host, and then they can run a Linux VM on that Windows host to run these machine learning models. But we're hearing the feedback for Windows, and we're working to support Windows as another deployment platform for our machine learning models. Another thing we're hearing is about ARM devices. And so in the same way, Azure IoT Edge does support running on ARM today. So you could create your own modules and deploy them onto ARM devices and run these modules. We also have this on our roadmap, in which we want to enable you to create Azure machine learning models that can then be deployed to ARM devices. And so that's something that we're working on, which is not released today. But today you are able to deploy and to run on x86 Linux devices. So just to make it a little bit more real, let's talk about some of the work that we've been doing with Jabil. Jabil as a manufacturer, and one of the things they manufacture is circuit boards. And so basically on an assembly line, for example, they would have circuit boards that come down to each assembly line step. Components are placed on the circuit board, and an AOI, or automatic optical inspection camera, is taking pictures of various components. These pictures are then sent to a human to look at. And so here are some sample images. A human would have a few seconds to take a look, for example, at the top set of images, and then that operator may say, okay, I'll pass this on to the next assembly line step. Maybe you see some pictures that look like the bottom. This would fail, and then you would fail it, rework it, etc., so that it doesn't keep on going down the line. So this is all fine and good. If you have just 6 or 7 images and you have a few seconds to look at them or to make a decision, no problem at all. But the thing with an AOI camera is that it might send an arbitrary number of images. And so you might have a situation in which, as the operator, you all of a sudden might see this many images. You might have to take a look and try to make a decision in the same amount of time. And excuse me. And in this case, this is what motivates a lot of the work that we do. Because when you have these images, when you have a fatigued operator, or an operator who might have, for some reason, might have not been looking at this specifically or carefully enough, it really motivates 3 things. First, it motivates the need for AI. really the ability for an AI model to take a look at these images and to be able to predict whether there's a manufacturing defect or not. The second part is the need for this to run on the edge, because for bandwidth concerns or for latency concerns, sending all of these images to the cloud just doesn't become, is just not economically or practically feasible because of the time that it takes to send these images and get a response back. So the second thing is this needs to run on a local device on the edge. The third thing that this motivates is the need for the AI to run fast. If you only have a few images, that's fine, but each image running through a deep neural network would require about 8 billion calculations to take a look through that image and to give you back a result. So 8 billion calculations for one image. Think about the number of images that might be coming off a circuit board. Think about the number of assembly line steps and the number of lines in the factory, and all of a sudden, the amount of compute required by these AI models is just overwhelming the compute that may be available. So this is where we start looking at what are some silicon alternatives for running these AI models, for running these deep neural networks. On the flexibility and efficiency scale you see here on the left are CPUs. CPUs are amazingly flexible. They can pretty much run anything, except they're sequential, and they don't run these AI models as quickly as other types of hardware. You have GPUs. GPUs are your graphical processing units, and GPUs are designed to do massive parallel processing. So GPUs today are the workhorses of AI. You have some data that comes in, and then you have a lot of parallel processing going on the chip, and then you're able to process it. And so these AI algorithms do a lot of things like matrix multiplies or a bunch of these different calculations. And so GPUs are well-tuned to process them. The thing about GPUs to consider would be just cost and just power consumption. On the far right here on the flexibility and efficiency scale are your ASICs. And ASICs are your application-specific integrated circuits. And these are chips that are custom designed for whatever workload that you have. And so if you think about these neural processing units, as we call them, basically the hardware that run these AI algorithms, there's basically two schools of thought. And the first one is the hard neural processing unit, which are essentially ASICs. And so you've probably heard about the Google TPU, Intel Nervana, Movidius, GraphCore. Cerebrus just announced a few weeks back a humongous chip to do AI. Amazon announced Inferentia, which is also coming out soon. But basically, a lot of these companies are building these specific hardened chips. The benefit of it, again, is that they do exactly what you want to do. The thing to consider about that is the time that it takes to be able to design a chip and test it and to tape it out, fab it, manufacture, et cetera, and get it into your data center could be about 2 years. Meaning that if we were to start today and create our own custom AI chip, we would not see it for about 2 years. And that's just the thing to consider when you're thinking about ASICs. So that's why, to keep up with the fast changing AI landscape, we're focusing on FPGAs. FPGAs being field programmable gate arrays. And so an FPGA is essentially reprogrammable silicon. There's a chip, and it has a ton of these compute engines. And each one of these compute engines is available for you to specify what the input is and what the output is. And you could configure the routing among all of these different compute engines. So the nice thing about an FPGA is that I could install this FPGA in the cloud or on the edge device, and I can update that over software. So I can run the model directly on the chip, which makes it super fast, and I can reconfigure it if I have an improved way of doing things. And this is where we're seeing the code design becoming very, very successful. Because if we had a fixed chip, if we were using a GPU, for example, or an ASIC, that hardware is fixed. I can't do anything about it. The only thing I can change is the software when I want to optimize my AI models. However, with an FPGA, I can optimize the software and the hardware. So giving me the benefit of co-designing these two things enables me to give you that best solution. And so the nice thing is that now I can reprogram the silicon, and I don't have to touch the hardware, and you get the latest and greatest in terms of the AI. So just to wrap up this section, in terms of what we're doing from an AI machine learning perspective at Microsoft, we have an AI platform with Azure Machine Learning. And it sounds like quite a few of you have already tried out and used Azure Machine Learning in the cloud. And some of you have actually also deployed that to edge devices, which is super exciting to hear. We're continuing the evolution of this platform to enable you and your data scientists to create these machine learning models and deploy them in the cloud and the edge. And we're also keeping an eye on the future, looking at the complexities of these AI algorithms and figuring out how to speed them up, putting a lot of effort into developing differentiated hardware such as FPGAs and the software stack on top of that, so that you'll be able to get the best, fastest, and most cost-effective AI and machine learning on the Azure platform. So with that, I'd like to thank you and turn it back to Robert to take us to the next poll question.
Ted, thank you so much for the introduction to machine learning. Really appreciate your insights. We would now like to collect more feedback and kind of understand what you're doing today with machine learning, and specifically what types of machine learning applications are you considering? So select one or more of the following, but are you looking for machine learning for computer vision, for workplace safety, for energy forecasting, predictive maintenance, or perhaps something else? You can select more than one, but please let us know your feedback on what types of applications you're looking to apply machine learning. I know there are many different types, so we also have other in there. Oh, great to see. So 78% predictive maintenance, that aligns well with what we're seeing. Also interesting to see a tie between energy forecasting and computer vision. We're seeing a lot of customers who see value in energy forecasting. And then of course, we showed you the Jabil example for computer vision. It's always a common favorite of how to use and apply machine learning. Also the other, we understand there's a lot of other use cases for machine learning, and it's hard to categorize all of them in easy buckets. But great feedback, really appreciate your perspective. And with that, we'd like to now transition and talk a little bit more about some case studies. So one example of an exciting case study is remote fueling for pumping and well site automation equipment. Even though the oil field is ultimately producing hydrocarbons for processed fuel, to keep these vehicles and heavy equipment running 24/7, they require and depend on processed fuel to be sent on site. A Moxa partner of ours, AWC, worked with one of the leading refueling companies in the Houston area to deploy a system that can help manage the deployment and billing for their refueling stations. A key benefit of this system is that it enables both the remote device management, but then more importantly, remote information about fuel consumption and the ability to offer higher availability and more reliable information for their metering. And so everyone understands that metering process directly impacts their billing. And so this real-time data and information can give them a much more reliable billing and a repeatable billing infrastructure. AWC worked with the end customer and a Microsoft partner to extend Moxa's Industrial IoT Edge Gateway in Debian Linux and add some key capabilities. The first was connectivity through Node S7, an open source protocol for connectivity to Siemens PLCs. Then, using Node.js, they added custom logic and the ability to communicate through a JSON buffer to the edge and then to Azure IoT Hub. Once this data is available in Azure IoT Hub, they stored this in an SQL database, and then they can run SQL queries to integrate the data coming from the edge with their internal billing systems. In addition, a Power BI dashboard provides real-time visibility so they can remotely monitor and manage hundreds of refueling vehicles spread across Texas, Oklahoma, and wherever else their customers rely on them for fueling service. This example was started before Azure IoT Edge was widely available. So our partner, AWC, built a lot of custom software, as I mentioned, with JSON. Going forward, this solution could easily take advantage of Azure IoT Edge to reduce complexity and increase the scalability of the system. Another common application, we've seen several deployments across different oil and gas customers in the upstream space, is for predictive maintenance of artificial lift systems. Now, to be fair, more commonly, these are referred to as pump jacks in the oil fields of Western US and Canada. And the pump jack is one of the oldest icons of oil and gas production. Today, with the scalability and the cellular-enabled deployment on our low-cost hardware, operators can connect existing equipment, in this case, using even Modbus Serial or TCP/IP, to modern Industrial IoT Edge Gateways, and then enable this integration into the cloud to create a single source of operation and maintenance information. If we look deeper here, these traditional pump jacks have a load cell, temperature, and motor, and they're often connected to a variable speed drive and a PLC. And rather than just replacing that entire existing control system, most of our customers add an additional Industrial IoT Edge gateway with cellular. They connect over legacy protocols to that existing system and then publish this data through Azure IoT Edge and Azure IoT Hub to their own cloud. In this example, pump jack is really a legacy piece of equipment, and monitoring this and controlling this is quite often hard. To be fair, they often don't even have a local user interface or HMI just because of the harsh environments. But with the addition of these new Industrial IoT Edge gateways, we can help you connect these legacy systems to the cloud. To go a little deeper and talk about the architecture, the block diagram is fairly straightforward. For this application, it looks similar to the one I showed you before for refueling, but in this case, we've got the Moxa Industrial IoT Edge Gateway, Moxa Industrial Linux, and they've also added a very important aspect, which is a TPM or Trusted Platform Module chip for security. And so this hardware plus specific software to store security keys really gives them a differentiated level of security, which is pretty important given how dispersed these assets are in remote locations. We then have Modbus software for connectivity, and then also many different types of customer-specific code. Then we use Azure IoT Edge to handle data communication to IoT Hub and also for remote device management. And really, if you take a look at this, Industrial IoT is not only about new products and solutions, it's really about connecting and modernizing existing equipment in the field at scales we have not been able to achieve in the past. And through that modernization, gaining new performance and scalability. So with that, and to conclude, I'd like to share a demo. And this is a pretty exciting demo that we've put together. What you can see here is this demo is located in Moxa's California sales and marketing offices. Given we're located in Southern California, there's plenty of sunshine, and so solar is a great choice for adding renewable energy. Here we've got some solar panels, as you can see in the picture, across both the building and the roof, and then also covering the parking spaces for vehicles. To help show the remote accessibility of IoT applications, we wanted to enable and track the energy production of our solar system. And so after a little research and help from our IT team, we realized that the solar inverter that's available on this system actually can communicate over Modbus. We then decided to monitor both the current and voltage, and then more importantly, we're also showing you the net energy production over time. And so as you can see, the flat line is during the night, and then the line that goes up is additional energy production during the day. You can also see different days where there might have been more or less sun, depending on the amount of net energy that was produced. We've then shown this all on a Power BI dashboard and allow you to remotely also log in and see what the weather is. This addition of the weather widget has had one downside. As we show this to key accounts across the Southeast and Northeast, we've realized the weather in Southern California is almost always 70 and sunny. And so for those of us in maybe Texas, where it's 100 degrees plus in the summer, or those of us in the Northeast with snow, it is a little bit of a harsh reminder of how nice the weather is for our colleagues there in Southern California. But still a great example of an industrial IoT application. And we're really excited to be able to share that and show customers the scalability you can achieve. So now we'll go back to our presentation. And what we'd like to do is really conclude this and thank Ted for his introduction to machine learning. I want to thank our audience, especially for joining us today and for all of your great feedback. And what we're going to do is we're going to welcome back Scott and open up for any questions you might have from the audience. We've seen a couple questions that were entered into the chat window while we were talking, so we'll address those. And then we encourage the rest of our audience to add additional questions as well. And so with that, I'll welcome back Scott, and Ted and I are glad to help answer some questions in the time remaining.
Fantastic, thank you, Robert. Yeah, so as Robert mentioned, we're going to address the questions that came in, and as he said, we have a few minutes left, so we do want to encourage further questions that we can address in the time remaining. So anyway, let's dive right in. The first question, are you able to deploy software OTA using cellular? Robert, do you want to take that one?
Sure, yes, we hear from all of our key accounts to be able to deploy various levels of software over the air using cellular as the network infrastructure is critical. And today we can do that through software containers. We're also working very hard on the capabilities to deploy direct updates to the Linux kernel. One thing to keep in mind though, and one of the things to understand that we're thinking of for reliability is if you were to have a power outage while you're updating the kernel, or if you were to see some network latency issues, you could lose connectivity to your device during a critical update. So we're also working on features that will have redundant flash capabilities so that even if you lose power, there's a recovery state so you don't lose connectivity to the device. But yeah, over-the-air cellular is one of our key requirements and careabouts.
Thank you for addressing that, Robert. The next two questions looks like these would be for you, Ted. So the first one is, when would you expect to deploy machine learning to ARM platforms?
Yeah, that's a great question, and it's something that is definitely on our roadmap. And we're hearing a lot about the requirements for these lower power ARM devices that customers also want to ingest data and to be able to run machine learning on. Unfortunately, I'm not able to share any specific timelines, but do know that we are very focused on it, and it's something that we hear from many of our customers.
Great, okay, and the second question for you is, do you support Azure IoT Edge for Windows?
For Windows, we are also working on that. That's also on the roadmap. We're working very closely with the Windows team to be able to support that. In the meantime, if you have a Windows device and it's something that you want to try running machine learning on the edge, some of the things that we've seen some folks do is spin up a Linux VM on that device so that it could run the Docker container. But also, just to note that for both ARM and Windows devices, Azure IoT Edge is still supported. So if you wanted to run other types of workloads where you're doing things like data ingest or streaming or your own custom functions, you can run them on your ARM and Windows devices. We just don't support that from a machine learning perspective today, but it's something that we're working very hard on.
Okay, great. Thanks for that feedback, Ted. Robert, this next one I believe is for you, and it's a good question. How do I deploy machine learning if I don't have data scientists?
Yeah, that is a great question. And maybe to build on Ted's comments, there's still a lot of capabilities today for stream analytics and data analytics at the edge. And we see a lot of customers deploying that. But yes, to extend into machine learning, there is that need for some data scientist expertise. And what I would actually say is we're part of the larger Microsoft ecosystem. And with several of our key customers, we've worked directly with Microsoft partners who have data scientists and have machine learning expertise. We've been able to benchmark their requirements on Moxa hardware and then work between Microsoft and their partners to help bring in that data scientist expertise. What I'd recommend for machine learning and really for any of these applications is that the customers focus on the business case and what they're trying to solve and make sure that it's more than just a proof of concept, but really it's something that can have a transformational effect on your business. And if that's the case, there are partners across the Microsoft ecosystem that Moxa can bring in and help you to solve some of these more complex applications. Of course, if you have your own data scientist, that's great. We're glad to work with them too. But we often run in a case where there just aren't enough data scientists, so that ecosystem becomes critical.
Right. Okay. Thank you, Robert. All right. We have time for a couple more questions. I think this is related back to poll question number one, but what is meant by IoT Edge?
That is a great question, and I think we have all tried to answer and address this question, and the reality is it really does vary. I'll cover it in two ways. We see the edge as scalability from hardware capability. For example, some people consider the edge to be 16 to 64 core processors that sit within a server that can exist outside of a centralized data center. And so that would be the edge. We focus a little bit more on what we call the far edge. And so these are devices that will sit out in your asset. Think about that pump jack, or sit next to a pumping station for natural gas. These type assets we call the far edge are gateways that can convert existing protocols to industrial IoT protocols and then connect to the cloud. There's also a middle ground. There's application for x86 quad core type processors, maybe even the Intel Atom family, that's kind of between that near edge, which is high massive compute, and that far edge, which is heavily distributed. There's been a lot of buzzwords around this area, but from our perspective, and when we meet with customers, it's really about what level of hardware performance do you want scaled across that near edge to far edge capability.
Awesome. Okay, thank you, Robert. I have another question for you, Robert. What device provisioning services does Moxa and their partners offer?
So we have integrated with Microsoft's device provisioning service, and that is actually a critical aspect because provides the scalability you need. Moxa is not in the business of standing up and supporting data centers. And so by integrating with the cloud and their device provisioning service, you can get the benefits of which data center you want to connect to. What we specifically add, which is critical, is you need to be able to have that device provisioning service actually communicate security keys all the way from the cloud to, for example, the TPM hardware chip embedded on our Moxa gateways. The APIs and the software infrastructure to do that is exactly what Microsoft and Moxa are working on and have been able to actually deploy at key customers, and we're continuing to expand it. The other thing we're looking at is how can we actually help transfer our hardware that's manufactured to your actual IoT hub or IoT cloud application, and how do we transfer that and transfer ownership through DPS. So I'd love to go deeper. This is a great area for us to meet in person and talk about, but the short answer is we have to heavily integrate with the cloud because the scale of the applications you need to address simply can't be solved by one vendor.
Okay, great. You know what? It looks like we have time for one more question. So we'll go with the question is, does Moxa work with Splunk?
It's a great question. Today, we do not work with Splunk. We're familiar with it and would be glad to follow up individually if there's some interest in that area, but there's not any specific integration with Splunk. Maybe that person could offline, feel free to send us an email and we'll make sure it gets to Robert.
Yep, for sure. There are a couple more questions, but we're actually out of time at this point, so we're going to close out the webinar. So Robert and Ted, thank you again for sharing all your knowledge and for your time today. There was a lot of information covered, so if anyone in the audience still has questions, please feel free to reach out to us at usa@moxa.com. Thanks again for joining and have a great rest of your day.